So back where we started. So that sigma over pi t to the fourth is going to play a major role in understanding the gas physics and whatnot. And then I've got the picture here of the black body spectrum, and yes, they're 2's, not z's. Okay, right. And so I'm not going to go through these next notes in any gory detail. I'm not going to derive them. They're standard stuff. This is basically mean kinetic energy, which is this portion of what I've talked about. So I just talked about this, and I showed you about this. Now we're going to talk about this mean kinetic energy. How do you calculate that? How do we know that is 3/2 kT? Well, it comes from the simple thing that you basically take this velocity distribution, okay, and you weight it by v squared, because what you want to get, what you want to do is you want to calculate this quantity basically, because that gives you the mean kinetic energy. So how do you do that? As with anything that you want to calculate, when you want to calculate a mean variable across some distribution, what you do is you weight the distribution by that variable. Okay, you may have seen this before. All right, if I want the mean of x, what do? I integrate x times the distribution of x dx, and then to make it so that I can take care of the distribution function itself, normalize it out, boom. All right, so basically if you want v squared, you basically are going to weight this by v squared. So your x becomes v squared, okay, and your x is v. And when you do that, you go through the algebra and you go through the calculus, lo and behold, you get that see it from here. Bless you.
Thanks.
Right there. Okay. So if you have the particles described by a single temperature, boom. Okay. Mean kinetic energy. That equation up there. Okay. Okay. Then you might want to know what the pressure is. Okay, and so without going through those derivations, okay, you can show that the mean pressure, okay, is the density over the mass times kT. Okay. Now that's for a given type of particle. Given particle. This is interesting. If you want the total pressure, right, then you have to sum up the partial pressures. Piece of I, if you will, okay? Mi rho I over all I, whatever, some number of particles. So you might have some particle that might have mass I, like hydrogen, helium, lithium, boron, carbon, nitrogen, oxygen. As you go up in I, okay, different masses, same T, different densities, because this is a mass density. Well, it turns out, folks, that the number density of some particle is the mass density divided by the mass. This is in grams per centimeter cubed. This is grams. So this is in particles per centimeter cubed. This is N. So what I'm saying is that there's a relationship between the number density and the rho. So if you know the number density of all your particles, and you know the temperature of the gas, you're in business. You can get the total pressure of the gas. sum up over all the particles, number densities of all the particles, boom, okay? It also turns out that P tote equals N tote KT. Because the K and the T pull out of the sum, and then you sum up all the NI's, you get the total density. N tote equals N sub I. Okay. Well, what if you don't know the number densities, but you only know the mass density? Now I want to make a distinction here. Because this is going to be important. Okay. Certain papers you're going to read, certain fields of astronomy, are going to talk about number densities. Particles per cubic centimeter, number densities. Okay. 10 to the 14 particles per cubic centimeters. Others are going to talk about mass densities. Okay. It is 10 to the 2 grams per cubic centimeter is the density. Okay. Well, to get the mass density of a gas is kind of complicated because each particle has its own mass. So to get the average, you're averaging over particles that all have different masses. It's very complicated. Okay, so I prefer to work in number densities because it's very, very straightforward. If I know the number densities of all my particles, I can get the total number density. I know the temperature of my gas, I can get the total pressure. I know the temperature of my gas, I can get the average kinetic energy if I want it. I know the temperature of my gas, I can get my radiation field. If I know the number density of all my particles, etc., I know the partial pressure of all of them. But it turns out that the equations are all much simpler in number densities. If you start using this, you have to get into something they're called mean molecular weights. Mean molecular weights came straight from the deepest depths of hell, okay, in my opinion. If you work with number densities, you don't have to use mean molecular weights. However, there are times when working in mass density is really actually advantageous. Say you want to calculate the actual mass of something, okay, or the omega relative to the density of something relative to the critical density. Well, that's in mass densities, all right? I will talk later about mean molecular weights, okay? But they effectively come from the fact that this mass and this density, they're changing in each of these sums, and therefore when you're adding this up over total all these masses, you have to account for some mean, if you will, based upon the distribution of particles in the gas. We'll get into that. We're going to have a section on calculating mean molecular weights. And trust me, you're going to see them in papers. You know, somebody's going to say, oh, I'm going to do this back of the envelope calculation to calculate something, and they'll say, and we assume a mean molecular weight of 0.6. Where does that come from? Why is that? Why? And not only that, but what does that 0.6 mean? You know, oh, that's sort of like a fully ionized gas that's dominated by only hydrogen and helium. Turns out you get a 0.6. Okay? Stuff like that. And soon you'll, you know, the more you work with the numbers, the more you'll know when you see a 0.6 of mean molecular weight what it means. Okay? I'm pretty sure I got that number right. Don't do any science with it. All right. So, everybody with me on that so far? Okay, so what I've done now is I've tried to describe to you the general thermal equilibrium condition, what happens when you have the thermal equilibrium condition, that we're considering a particle field and a radiation field, that they're in complete equilibrium, that have total detailed balancing. We have a relationship for the temperature and the pressure, okay, that you see here. Okay. You might call it equation of state. Okay? So, what we're going to now embark upon is some definitional descriptions of gas particles in a gas. And why? Because I'm going to have you model some gas conditions. I'm going to give you a density and a chemical composition, and I'm going to give you a temperature, and I'm going to say, calculate for me the ionization balance of these particles. Okay? And you eventually are going to want to take that information, and we're going to put it into a gas that varies with some kind of scale height to see how the ionization changes with height in some type of gas. Starting to sound like an atmosphere. Okay? And then we have to put some boundary conditions on that, and voila, you get a stellar atmosphere. All right? And as you all know, that's the final project. So we're going to do step by step on these calculations. Okay? So I'm going to define for you some new things. First, I'm going to define for you the particle field in detail. Second of all, I'm going to define for you things called ionization fractions and whatnot. Just feel like it's a disaster that those videos have been dying out. Okay. All right, we are on number densities, mass densities, and mass fractions. Okay. So, right. Let me define some things for you. N of capital N, rho of capital N, N sub E, and rho sub E. Okay, what do you think this is? Okay. This is the number density of all particles, well, look this way, all nuclear particles. Okay. That means all elements on the periodic table that have the nuclei, right? Basically atoms, whether they're neutral or ionized atoms. If they have a nucleus, whether they're a bare nucleus without electrons, doesn't matter. That's the number density of them. This is the mass density of all nuclear particles. This is in centimeters minus 3, or particles per centimeter minus 3. This is in grams per centimeter minus 3. N sub E, anybody?
Number density of electrons?
Right. Of the free electrons in the gas. Centimeter minus 3. And rho sub E, number density, number density, and this is the mass density of free electrons in the gas. That's our starting point. So when we want to model a gas and quantify a gas, our starting point is that we're going to want to know what the total number of nucleons are. In a sense, that kind of defines the gas. That's a boundary condition on the gas conditions, actually. Okay, so having done that, we're going to define N of I, J, K. You're can see it. Triply dimensioned arrays in my code. Oh no. Well, we won't get too hot and bothered about excitation levels. I is excitation. J is ionization stage. And K is what species you are. Okay? K equals 1, hydrogen. K equals 2, helium. In a sense, it's the Z number, or the atomic number. Okay. I equals 1, ground state. I equals 2, first excited state. Dash, 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 dash. J equals 1, neutral. J equals 2, first stage ionized. In other words, -1 electron. J equals 3, etc. Okay? So by defining IJK, we have a full description of every excitation state for every ionization stage for every species. Okay? Now, let's look at some simple sums. There is something that we call number density conservation. Just to break things up. Okay? Number 1, if you sum in drat. You have to tell me whether this is visible or not. If you sum Nijk over all I, okay, that is equal to Njk. What? Yes. Let's take carbon. Carbon's K equals 6. Let's take carbon that has 2 electrons missing. So that's J equals 2. Okay? Of those carbons in the gas that have 2 electrons missing, some of them are in the ground state, I equals 1. Some of them are in the first excited state, I equals 2. Some of them are in the third excited state, I equals 3, and so on and so forth. And some are fully ionized. Okay? If I sum up all of those in the various excitation states, guess what I get? All of the doubly ionized carbon. I get all of the K equals 6, J equals 2 atoms in the gas, summed up over all their excitation states. Okay? So, if J is 2 and K is 6, I get all the number density of all of those, no matter what their ionization, or sorry, no matter what their excitation stages are. Summed them all up.
Hey, Chris?
Yes?
Sorry, I think I may have missed this. What is the capital J thing?
I was just getting there.
Oh, okay.
All right. If you've got carbon where K equals 6, how many J states, how many J levels are there? How many electrons are there? 6. J equals 1 is the ground, that's 6 electrons. J equals 2, okay, that is 5 electrons, 3, 4 electrons, 2, 3 electrons, 1, 2 electrons, 4, 3 electrons, 5, 2 electrons, 6, 1 electron, 7 0 electrons. Does everybody get that? This is neutral. First ionized, 1 electron missing, 3 times ionized, 4 times, 5 times, 7 times you can ionize it. So JK is equal to K plus 1. Did I make sense on that? Because this is the fully ionized bare nucleus. So 1 is neutral, has all 6 electrons. You can remove the 6 electrons. So here's 6, remove 1, that's J equals 2, remove 2, 3, that's J, remove 1, that's J equals 1, you remove 2, that's J equals 2, you remove 3, blah, 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 blah. And then you get to the point where you're fully ionized. Okay. All right. Does everybody get that? Well, guess what? If you sum up the NJK, what do you get? Right. And so the question becomes, how many are there? I was wondering why I was getting confused faces, and now I totally get it. I totally screwed up putting the JK on that sum. So, back up. This is to infinity, and this is to JK. I'm so sorry about that. You have an infinite number of n levels in hydrogen, right? You're summing up over all the excitation states. Yes, sorry about that. Do you forgive me?
No.
Thank you. Heard one. So this is a sum of all excitation states, which gives you, say, K6, J equals 2, doubly ionized carbon. Okay. If you take all the doubly ionized carbon, or I'm sorry, if you take the carbon in all the different ionization stages. Okay. Carbon is neutral, carbon that's once ionized with 1 electron, 1 carbon that's twice ionized. Carbon. You add them all up, you get the density of all the carbon. Then, if you sum up
Hey Chris?
Yeah.
So you said that the capital JK is K plus 1 you have written up there.
Yeah.
And you mentioned that it was just the number of times that you can ionize.
Well, it's the plus 1 is because you're setting J equals 1 as the neutral state, where it has all 6 electrons, or all 7 electrons, or all K electrons.
Okay, so why wouldn't capital JK just be equal to the largest J value? Like the largest lowercase j value.
The largest lowercase j value is JK, capital J.
Oh,
K.
oh, it is. Okay.
Yeah.
Okay.
That's as big as the sum can go.
Okay.
Yeah.
Okay.
So for any ion, say hydrogen, you can ionize, it can be neutral, little j equals 1, or it could be ionized, little j equals 2. That's as big as it can get, which is, because K equals 1 for hydrogen, that's K plus 1. Let's go to helium, same story. Neutral, J equals 1. First ionized, J equals 2. Twice ionized, which is the highest it can go, J equals 3. Since K is 2 for helium, JK equals K plus 1. Maybe that was clearer than my other example. Okay. All right, so now if you take, say, all of the hydrogen, all of the helium, all of the carbon, all of the nitrogen, and you sum all of those number densities, you get the total nuclear number density. Okay? Because basically you're just saying, oh, I've got a density of hydrogen, I've got a density of helium, I have a density of, and I'm just going to take all of those and it gives me the total number density. We're doing number densities, that's why this works so cleanly. Okay? The number per cubic volume. Okay. Are there any questions about that? Okay. I think that might be a good place to stop, because the next stage is to talk about actual abundances and abundance fractions. And you'll notice in the table these numbers which give you the abundance, relative abundances of all the atoms in the sun, in the stellar atmosphere of the sun. But they're in kind of strange numbers on a scale of 12 for hydrogen in the log, which is, you know, maybe a little weird, so we're going to talk about that, and then how you take this table and unfold it into number densities. That's what you need to know. I mean, if you're going to go look up some table and it's in numbers like this, and you want to model a gas, you're going to need to know how to convert it, so we're going to talk about that next. And then we're going to go back into not talking just about number densities, but we're going to go into talking about mass densities, because it turns out that a lot of formalism is in terms of mass densities. Okay? All right. That terminates today's lecture.